Welcome to Johnson Supply, verification of heat pump operation, level 1. This is a very common design for heat pump operation or engineering data for a heat pump. A few things to point out, we have the high temperature at 47 degrees and the low temperature at 17 degrees. These two temperatures are common for the high and low output of heat pump operation. As part of a verification, we're going to use a version of this formula. BTU equals our delta T times our cubic feet per minute times 1.08, which is our specific heat of the air at sea level. Again, the CFM is the CFM plotted on the fan tables or shown by your system display. The delta T being the dry bulb temperature change through the system, normally measured at the input and the output of the equipment. The 1.08, our heating BTU multiplier at sea level, is the specific heat of our air over our CFM 0.24 times our 60 minutes in an hour. This factor will vary at higher altitudes and temperatures. During our verification, we'll change the formula and use a version of delta T equals our BTUs divided by the cubic feet per minute times our 1.08. We start by looking at the engineering data. We'll change our formula to find the temperature rise. We'll first take the BTUs of 23,200 and our cubic feet per minute. In this example, we have a 2-ton unit at 400 cubic feet per ton. Will give us 800 cubic feet per minute. And doing a little bit of math, we'll find that our temperature rise at 47 degree outdoor temperature for this piece of equipment is 26.85 degrees. And our low temperature of 17 degrees, we'll have 12,600 BTU output. We'll still have our 800 cubic feet per minute. That'll give us a delta T for this unit at 17 degrees of 14.58 degrees. Using another example of a 4-ton unit, at 47 degrees, or our high output, we'll have 44,500. And our cubic feet per minute on a 4-ton would be 400 cubic feet per ton, will give us 1,600 cubic feet per minute. We'll have a delta T at 47 degrees of 25.75 degrees. At an outdoor temperature of 17 degrees, we'll have 28,000 BTUs. Our CFM will remain at 1,600. We'll have a delta T of 16.21 degrees. For a moment during verification, we'll talk about the COP and the amp draw of the equipment. You'll see at our high temperature of 47, we're drawing 13 amps. So an electric element of any wattage has a COP of 1.0. In this example, at 47 degrees, the heat pump has a coefficient of performance of 3.86. So for every 1 BTU produced by the electric heat, the heat pump will produce 3.86 BTUs. At a -5, the heat pump will still produce 1.56 BTUs compared to the electric heat producing 1 BTU. We can also see the coefficient of performance appear on the compressor motor kilowatt input. So the total kilowatt output, the blower will be used in either operation, so for the comparison to the electric heat, the blower wattage will not be added. Our total kilowatt output chart shows the output divided by the input is an equivalent of a coefficient of performance. At 47 degrees, 13,500 total kilowatts divided by the 3,330 input will give us a COP of 4.05. At 17 degrees, we would have a COP of 2.99. At -5 degrees, we would have a COP of 2.3. In this example, we see at 47 degrees, the amp draw is 13, and as we swing the -5 degrees, the amp draw drops to 6.2. As the temperatures get lower outdoors, the pressures of the refrigerant also lower, making the compressor draw less amps in order to produce the heat output. And now a little more math, finding the BTU for any degree. So we're going to subtract our low from our high and divide by the difference. So we'll do that in a few spots. Our high output is 44,500. Our low output is 28,000. The difference is 16,500. And the temperature at 47, subtract 17 for the low, is a 30-degree difference. So our 16,500 difference divided by our temperature difference of 30 is 550 BTUs per degree. So at 41 degrees, the outdoor temperature is 6 degrees below the high. The unit will have the 44,500 minus the 6 degrees times the 550 BTU per degree, or 44,500 minus 3,300. So the BTU output would be 41,200. Putting that in our formula with the CFM remaining at 1600, we find at the 41 degree outdoor temp, the delta T expected would be 23.84 degrees. This is another example we have of a heat pump performance chart. And here we see the high temp and the low temp heating capacity are listed without a temperature. When we see the high temp and low temp, the high temp is always 47 degrees and the low temp is 17 degrees. And for a quick note, on this chart we also see the C rating and the EER rating. The EER is the total number of BTUs divided by the total number of watt hours. EER can be done at that moment. On a cool morning compared to a very hot afternoon, the EER would be much better. The CER is the total number of BTUs divided by the total number of watt hours over a season of operation. It takes into account how many hours were expected to run at low temperatures and how many hours were expected to run at the high temperatures. Back to our chart. The high temp and the low temp shown in the picture here on this 1.5 ton heat pump are 17,800 and 11,400. On a 1.5 ton system, we expect to have a cubic feet per minute of 600. In this example, the high temp, 17,800 divided by the 600 cubic feet times the 1.08 will give us a delta T expected of 27.47 degrees. The low temp with the CFM, still 600, would expect the delta T at 17.59 degrees. This is another example of a heat performance output. The heating capacity chart shown does not show the 47 and 17 degrees, but shows the output at 5-degree increments. In this example, the 45 degrees would produce 39,600, and the cubic feet for 3.5 ton would be 1,400 cubic feet. Using our formula, we expect a delta T at 45 degree outdoor temperature of 25.85 degrees. Doing the same for 25 degree outdoor temperature with an output of 28,600, we would have 18.19 degree delta T. If we do a little bit of math, we'll find 20 degree difference divided by our BTU difference of 11,000 gives us our 550 BTUs per degree. So if we take that 45 up to 47, we would add to 550 twice. We would see a delta T of 26.91 at our 47 degree outdoor temperature. At our 17 degree outdoor temperature, we would expect the delta T of 16 degrees. This is another very popular style of heating capacity output chart. This one does show 5-degree increments, but it also shows a 17 and 47 degree rating for high and low. This one does give you the cubic feet suggested by the manufacturer. In this case, the 2.5 ton is rated at 400 cubic feet per ton, or a total of 1,000 cubic feet per minute. Following our formula with the output of 29,400 and the CFM of 1,000, our high output would be delta T expected of 25.2, and our low output with 18,600 would have a delta T expected of 17.22 degrees. Now, if we've combined all these different units, 1.5 all the way to 4 tons from Goodman Lennox the Train, you could see on a high output, or 47, the delta T on a heat pump most commonly is about 26 degrees. And at 17 degrees, the low output is about 16 degrees. This is an approximation of what you can expect to see. So your delta T at 400 cubic feet per ton and rated at 47 for high would have a delta T of 26.44. As you follow the chart, down to 17, we'll have our output of 16.32, and at 0, most heat pumps are going to produce a delta T of 10.59 degrees. With the same piece of equipment at different cubic feet per minute, with the indoor blower, we'll find at 1,000 cubic feet for this piece of equipment with a 29,400 BTU output would have the expected 25.2 degrees. If we were to increase the CFMs to 1,200, we'd have the same BTU output of 29,400, but our delta T is 22.68. Lowering that slightly to 1,100 would still give us a delta T of 24.74. And if we lowered it down to 900, we'd have a delta T rising all the way to 30.24 degrees. So all we do is move heat. During the heat pump mode, we are extracting heat from the outdoor air, and the blower removes the heat or extracts it from the refrigerant and releases it in the airstream. The indoor coil becomes the unit's condensing coil. Low airflow across the condensing coil will cause an increase in head pressure. During the heat pump mode, the indoor coil acts as the condenser. The manufacturer recommended airflow should be followed. Restrictive filters act as plug condenser coils due to an air conditioner. Verify airflow. External static pressure measurements should be part of everyday test procedure.
Okay, so let's break this down here a little bit and answer this question. How do I test ESP, or external static pressure? Well, we'll go through some slides here and show you some examples of static pressure, what it looks like, and some real easy ways to test it out in the field. Okay, so this chart here is going to show us exactly what external static pressure looks like. If you'll notice on the return grill over on the upper left hand side, you'll see we begin our airflow there. And as you see that airflow travel through the ductwork back to our piece of equipment, you will also notice those little arrows on the side of the duct pointing in a perpendicular direction to airflow. That is our static pressure. Static pressure is pressure that is exerted on the outside of the duct perpendicular to airflow. And if you think of that on the return side, we have air pressure in that duct that is below atmospheric pressure. So our static pressure is going to be exerted towards the center of the duct. That's where we're going to experience our resistance. And that static pressure will be measured in inches of water column. We will have a resistance to the ductwork. Our return air grill will also provide us with some static pressure resistance to airflow, as well as the air filter, whether it be a media cabinet or just a 1 or a 2 inch thick filter. anything in the path of that airflow or that air stream is going to provide some sort of resistance to airflow, and therefore will be considered in our total external static pressure that we measure at the inlet of the blower wheel on that piece of equipment. You can see right after the air filter and below the blower wheel we are taking a static pressure reading. That's where we will want to take our return air static. And why do we take it there? Well, we need to figure out what the total external static pressure is on everything in the return air duct. The filter, the duct, the turns, the sweeps, the grills, all of that combines to give us a total external static pressure, or our resistance to airflow in that duct. Now many times you don't have that nice little section of duct between the air filter and the blower wheel, so sometimes this measurement needs to be taken in the blower compartment or the blower cabinet of your air handler or your gas furnace, whatever you're dealing with there. Over on the supply side of things, you can see that our air pressure is going to be above atmospheric pressure. So you see that our external static pressure is pointing out away from the airflow. See, it's pointing towards the outside of the duct. Once again, this is in a perpendicular direction to the airflow. And we want to get a measurement right after our piece of equipment. So we want to get a measurement before a comfort cooling coil. This example here is a gas furnace, so our cooling coil, or our DX coil if you will, is going to be external to that cabinet. Now if I had an air handler or maybe a package unit, this coil would be internal within the cabinet of my equipment. It would not be considered in my total external static pressure. So once again, the ductwork is going to give us a resistance to airflow and give us a static pressure amount. Our comfort cooling or heating coil is going to give us that resistance, as well as our takeoffs, our pipe, our registers, or diffusers are going to give us a certain amount of static pressure. And that's what we want to measure right at the breech or the outlet of that piece of equipment. That way we can accurately measure in inches of water column the static pressure of all those components added together. If we know our total external static pressure, then we can calculate airflow based on the fan performance data of the equipment that we are testing. The following example is that of a gas furnace with an external coil. The same process would be used for an air handler or even a package unit for that matter, only the coil would be internal to our equipment rather than external, just like we discussed in the previous drawing. Okay, this is a fan performance data chart from a particular equipment manufacturer for their particular piece of equipment. And these can be obtained usually off the manufacturer's website, or a lot of times you will see them in the installation operation manual for that piece of equipment. And this is a pretty standard chart. Over on the left, you will see the model numbers of gas furnaces listed. You will also see a column for the motor speed taps that are being used. This particular example is for a PSC blower application, a permanent split capacitor application, where we have 4 designated speed taps. And you would see a similar chart to this if you had, say, an X13 or a multi-tap ECM motor. The change in airflow wouldn't be quite as great in relation to static pressure, but you would see a very similar chart being used. Across the top of this chart, you will see the external static pressures listed in inches of water column, and then you will also see the corresponding airflow listed in CFM, and in some cases you'll even see a temperature rise listed. So what this chart is telling us is that the equipment manufacturer tested each piece of equipment specifically at a given constant static pressure, and that is the corresponding airflow at that static pressure. So you know if you have a given piece of equipment at a given static pressure, you know exactly what the airflow is going to be. It's a very helpful chart in calculating both airflow and static pressure. Okay, so something you will see on every piece of equipment is a unit nameplate, whether it be a gas furnace or an air handler, package unit, what have you. And on this nameplate, you will see the maximum external static pressure at which this equipment was tested and rated. Now, in a gas furnace, most of them are about 0.5 or half an inch of static pressure. Air handlers and package units can kind of vary. But this information is included on the nameplate. Okay, so once you have the correct fan chart for your particular piece of equipment, now all we need to do is determine our total external static pressure. Once we have that total external static pressure, we can use our fan chart to determine our exact airflow of the system. Okay, so we'll take a look at our first example here, and this is a Goodman gas furnace model GMS 80453, and we're using that on the high-speed motor tap, and we take a static pressure reading, and you will see that we measure our total external static pressure at 0.5 inches water column. Now you'll notice in that previous chart where your return air static would be a negative value, and that your supply air static would be a positive value. So these values then, as far as above or below atmospheric pressure, are disregarded because that negative value of the return air is still a force that works against the blower wheel. And that's really what we're looking for. What is the force that is acting against that blower wheel? So we just disregard the positive, negative values, and we add the measurements together. For example, I think we had like a 0.3 and a 0.2, so we would add them together to 0.5. It wouldn't end up being like a 0.1 where they cancel each other out because both of those forces are still acting against the blower wheel. So our total external static pressure is 0.5. We plug that into our chart on the high-speed tap, and we come up with 1,344 CFM. This is an accurate way of knowing what your airflow is based on static pressure. So let's take a moment and just break this down a little bit further in checking static pressure drop. A component's resistance can be found by measuring the static pressure drop across it. Remember, we said that each individual component in that duct system had a resistance to airflow. And we can pin that down and isolate those individual components and check the static pressure of them with our static pressure tips and our measuring device, whether it be an electronic manometer or an incline manometer or magnehelic. So this is what I like to call a typical total external static pressure layout. Sometimes this is referred to as a static pressure budget. Now remember, in the example that we previously looked at, our total external static pressure was 0.5. Okay, 0.5 inches water column, resistance to airflow. Now what does that look like? Okay, this is a breakdown of what you will typically see in a residential split system for static pressure. Our return duct static should ideally be about 0.10 or a tenth of an inch, and that should make up 20% of our total external static pressure. So then you can plug whatever numbers you want into this. Like if your system's designed to run at 0.8, then just 20% of that is going to be what your return duct static is going to be. Supply duct static, again, 0.10 or 20% of that total external static pressure. Our air filter static pressure. Air filter static pressure should be no more than 0.10 or 20% of your total external static pressure. And this is where we see a tremendous amount of variance out there in the field. A lot of times you'll run across air filters that are either the wrong material, they're too small, or just a variety of different combinations of those things. And sometimes you can end up with 0.3, 0.35 static pressure drop across a clean air filter. And that just really, really inhibits the performance of our system, really slows down our airflow. So that air filter static is critical. Make sure that that stays no more than 20% of your total external static pressure budget. Now we have a cooling coil in here that's external to our equipment, and that was at 0.20 inches water column, or 40% of our total external static pressure budget. And that's where we end up at 0.5. It's a combination of all of those things. So if we were to test the return static on this particular system, we would be measuring the resistance of the air filter and the return duct static. So we would probably have a return air static measurement of 0.2 inches water column, 0.20 inches water column. On our supply side, we would be measuring the cooling coil and the supply duct static pressure, which 0.20 plus 0.10 would give us 0.30. So you'd have 0.20 on the return, 0.30 on the supply. That would then net us out to our 0.50 external static pressure. If any of these external components has an excessive resistance to airflow, it will be indicated by a higher than normal static pressure reading. Example of, say, plugged filters, or, as we said previously, improper sized air filters, improper material, or too small or restrictive ductwork. If we have registers that are blocked or dampers that aren't opening correctly, all of these things will contribute to higher than normal static pressures and will then have an adverse effect on our airflow as well as system performance. So when testing total external static pressure, again, remember you're testing the entire system, not just the piece of equipment or that box that's in the mechanical room. You're really looking at the system as a whole. Every grill, register, diffuser, piece of duct, takeoff, transition matters. All of these components add up to give us that total external static pressure. And by using these static pressure readings, we can not only determine if we have the correct amount of airflow in the system, but if we don't have the correct amount of airflow, now we can look at those readings and look to see where we have higher than normal static pressures and what component is giving us that higher than normal static pressure resistance or drop in the system. It's good to keep in mind the whole system, just as this chart indicates, because it all has to work together. Sometimes it's rather easy to just focus on the piece of equipment, especially on a higher end, inverter driven, more efficient piece of equipment, to focus on the shiny box. And we can quite easily overlook the delivery system. If we put a very high end, very efficient piece of equipment, made it up to a poor delivery system, we will end up with a poor system. The greatest, most technologically advanced piece of equipment in the world cannot overcome a poor air distribution system. Remember, without air, we have no air conditioning. Without air, we don't have any forced air heating. So those are all things to keep in mind when commissioning, as well as diagnosing heat pump and other forced air systems.